Yesterday evening at 7 p.m. Eastern Time, solar physicists at NASA's Solar Dynamics Observatory detected something that made them sit up straight. A sunspot region designated AR4321 had transformed overnight into what they call a beta-gamma delta magnetic configuration. If you lived through the solar storms of 1989 or the Carrington event discussions, you know what that means. Welcome back. On December 24th, Christmas Eve morning, AR4321 emerged in the sun's southwest quadrant. Nothing unusual at first, just another dark patch among dozens that pepper our star's surface constantly. But within 24 hours, something changed. The magnetic field lines beneath that region twisted, compressed, and reorganized themselves into the most complex configuration we classify: beta-gamma delta, the kind that produces X-class flares. What makes this particular sunspot noteworthy isn't just its magnetic complexity, it's the timing. We're officially past solar maximum now, the peak of the sun's 11-year cycle. Activities should be winding down, yet here's AR4321 defying the script, growing more energetic while its neighbors fade. The sun, it seems, didn't get the memo about retirement. NASA's helioseismic and magnetic imager captured the development in real time. The images show something fascinating: opposing magnetic polarities crushed together in a relatively small area, less than 100,000 kilometers across. That might sound large, but on the sun scale, it's compressed tight, unstable, like a coiled spring waiting to release. Here's what you need to understand. When magnetic field lines with opposite polarities get forced together like this, they eventually reconnect violently. The energy released in that reconnection doesn't dissipate gradually, it erupts. Plasma heated to tens of millions of degrees gets hurled into space at speeds approaching 3 million kilometers per hour. That's an X-class solar flare. Now, before you start preparing your bunker, let's put this in perspective. The sun produces flares constantly. C-class flares, minor ones, happen multiple times per day. M-class flares, moderate events, occur several times per week during active periods. X-class flares, the category AR4321 could produce, those are rarer, maybe a few dozen per solar cycle. But here's the question I want you to think about. How prepared are we really? In 1859, the Carrington event, the most powerful geomagnetic storm in recorded history, struck Earth. Telegraph systems caught fire. Auroras appeared as far south as Cuba. Some operators could send messages using only the current induced by the storm itself. No batteries needed. That was impressive when our entire electrical infrastructure consisted of telegraph wires. Today we have power grids spanning continents, satellites controlling everything from GPS to financial transactions, undersea cables carrying the internet between nations. What would a Carrington-level event do to that infrastructure? Write your answer in the comments. Some experts say weeks of blackouts. Others say months. The truth is, we don't entirely know because it's never happened in the modern era. AR4321 probably won't produce a Carrington-level event. Probably. The odds are low, but it demonstrates something crucial. The sun is always capable of surprise. Solar physicists monitor at 24/7 precisely because we need advance warning. Current models give us maybe 18 to 24 hours between detecting a major coronal mass ejection and its arrival at Earth. That's our window to safeguard satellites. Alert power companies. Prepare. The European Space Agency's PROBA-3 mission, which just began operations this year. adds a new dimension to this monitoring. 2 spacecraft flying in precise formation create artificial solar eclipses on demand, letting scientists observe the corona, the sun's outer atmosphere, where these eruptions originate. Before PROBA 3, we could study either the solar disk or the distant corona, but not the critical region between them. Now we can. That gap is exactly where coronal mass ejections form and accelerate. Here's something they mentioned quietly in the December 26th space weather forecast. Geomagnetic activity could reach G2 storm levels by December 30th. Not from AR4321 specifically, but from a coronal hole that rotated into Earth-facing position last week. High-speed solar wind streams are already buffeting Earth's magnetic field. If AR4321 releases a major flare now, while our magnetosphere is already disturbed, the combined effect could be significant. What does significant mean practically? Aurora visible as far south as Michigan, maybe Pennsylvania, possible GPS disruptions, radio communications affected, especially high-frequency bands that airplane pilots and ships use for long-distance contact. Satellite operators put spacecraft into safe mode, turning non-essential systems off to reduce risk. Power grid managers in northern latitudes prepare for potential fluctuations. Nothing catastrophic, nothing civilization-ending, but enough to remind us that we live on a planet orbiting an active star. And sometimes, that star flexes its muscles. You remember the aurora displays from November, don't you? Some of the most spectacular northern lights in years, visible as far south as Mexico and Florida. AR4321 has the potential to deliver something similar if conditions align. And here's what's interesting. We're getting better at predicting these events. Not perfectly. Space weather forecasting isn't like terrestrial weather yet. But better. The models improve the spacecraft monitoring the sun multiply. The international coordination strengthens. That coordination matters more than the technology sometimes. When the Solar Dynamics Observatory detects a major flare, that data gets shared instantly with NOAA's Space Weather Prediction Center, the European Space Agency, space agencies in Japan, China, India, dozens of research institutions. Within minutes, forecasters worldwide analyze the same information, model the potential impacts, issue alerts that didn't exist 20 years ago. AR4321 will either erupt or it won't. By the time you watch this, we might already know. The sunspot rotates with the sun's surface, moving gradually out of Earth-facing position over the next week. If it's going to affect us directly, it needs to happen soon. After that, any flares will spray into space at angles that miss Earth entirely. But here's the real question, and I want to hear your thoughts on this. Should we be investing more in space weather infrastructure? Not just monitoring, but protection. Shielding for critical satellites, backup systems for power grids, protocols that go beyond wait and see. The technology exists. The engineering is understood. What's missing is often political will and funding priority. Some argue it's unnecessary, that major solar storms are too rare to justify the expense. Others point out that rare doesn't mean impossible, and the cost of protection is far less than the cost of recovery after a direct hit. Where do you stand? Is this something you think about? Or does it seem too abstract? Too unlikely? AR4321 is fading now as I record this. The magnetic complexity remains, but the region itself shrinks slightly day by day. In a week it will rotate over the sun's western limb. invisible from Earth. Perhaps it will erupt on the far side and we'll never know. Perhaps it will complete a full rotation and reappear on the eastern limb in 2 weeks. Still active, still dangerous, or perhaps it will simply dissolve, its magnetic field relaxing, the energy dissipating harmlessly into the corona. That's what happens most of the time. The sun threatens more than it delivers. But not always. The sun has been doing this for 4.6 billion years. It will continue long after we're gone. Our job, our responsibility really, is to pay attention, to watch, to prepare, because eventually, not if, but when, another Carrington event will occur, another solar storm powerful enough to overwhelm our defenses, will strike Earth. The question isn't whether, it's when, and whether we'll be ready. Thank you for watching. If you remember the solar storms from decades past, the ones that disrupted radio or created unexpected auroras, share your experience in the comments. And if you think we're either overreacting or underreacting to space weather threats, I want to hear that too. Until next time, keep watching the skies, especially the sun.